You can start. Well, I have 450 millimeters of mercury. You're going to do this exactly the same as we've been doing. Millimeters of mercury's got to go on the bottom. Centimeter of water's got to go on top. How many millimeters of mercury in 1 atmosphere? Thank you. How many centimeters of water? All I'm doing, this is 1, isn't it? In essence, you're using a conversion factor. So 450 times 1034 divided by 760. 612.24 centimeters of water. Okay? Everybody follow where I did that? I just set it up as a ratio. Oh, look at that. Okay, so Dalton's Law was talking about the sum of the partial pressures equal to total Total pressure is a mixture of the individual partial pressures summed up. Or each I'm stroking out. You sure we're taking my blood pressure correctly there earlier? Not that you can remember what the number was, but each gas exerts a partial pressure that is determined by its concentration. And it's just that total pressure times your fractional concentration. So here's an interesting one. What is the total pressure in a dry gas mixture given the following information? PO2 is 150, nitrogen is 500, anesthetic gas is 8. Let me just add them up. 658 millimeters of mercury. Probably don't realize this, but when they give you anesthesia through an inhalational anesthetic agent, like nitrous, it exerts a partial pressure the same way as any other gas does. And that's how they regulate how much is being delivered, is by regulating the percentage of anesthetic gas that is utilized. And dry, again, implies that we're not taking into account water vapor. This is just, again, dry gas, so I don't have to worry about water vapor. 700 times 0.6 is 420. Okay.
Calculate the partial pressure of oxygen in a dry gas at a barometric pressure of 704 and an IO2.
So I'm telling you that it's at 60%. So I'm also telling them that we're going to consider this a dry gas, that there's no humidity.
But it's fractured inside of O2.
Okay. How about this then? Would that confuse you less?
Yeah.
Okay.
Now, where you just gave me the value of
0.6. So I multiply 0.6 times my barometric pressure. This is Dalton's Law. That's all it is, yeah.
How much of that 700 is your oxygen?
60% of it.
Yeah. So you're trying to find out what.
So 60% of 700 is 420.
So if it wasn't a dry gas, we would subtract.
We would have to account for water vapor.
Okay.
I'm just saying that right here at my mouth, before I inhale it, how much is it?
Okay.
Normally we do account for water vapor, and we know that at the fully saturated point, that isothermal saturation boundary just beyond the carina, we're warm to 37, we're humidified to 100%, and the key one we want to remember here is that it yields a partial pressure of 47. Now, we haven't talked yet about this, but there's also a content, a density that it has, oh, there's that word again, where we can express it in milligrams per liter. And the value is technically 43.9, we call it 44 milligrams per liter as far as how much actual water is there. Now, we're going to come back and visit this when we talk about humidity and talk about how we can alter the amount of water that is in the air. Okay. So we need to make sure that if we want a truly a dry gas, we've removed all the water vapor. Otherwise, whenever we see the word I, as Mary Kay pointed out, we have to subtract off 47. Now, in reality, this room does have humidity. It's not a totally dry room. So there really should be something we should account for, but for our purposes, we're not going to worry about it. And this is just talking about, okay, so now I have a barometric pressure of 730. What is the partial pressure of an anesthetic gas if my PO2 is 150, my water vapor is 47, and my nitrogen is 480? So what I would need to do is subtract off the 150, the 47, and the 480 from the 730, and what is left is what the anesthetic gas is taking up. I backed into it. It's an application of Dalton's Law. Okay? Barometric pressure is 650. What's the partial pressure of nitrogen if I'm breathing room air in the alveolus? Got to take away the water vapor, got to multiply times 0.78. And that's what it'll end up being. Nitrogen's concentration is 0.78 in room air. So the water vapor that is present is dependent upon a couple different factors. One is the temperature of the gas, and one is the relative humidity, the percentage saturation that gas is. Now, there is charts like this that you would be given. This is from Egan. And you'll notice that at a temperature of 37, this very last entry, there's my partial pressure, 47. We got 43.8. We said it was 44 milligrams per liter. As you get cooler, those values fall. Okay? So water vapor that is present is dependent upon the temperature of the gas. These are all assuming that it's fully saturated. So at a temperature, let's say, of 30, at 100% saturation, be 31.8 millimeters of mercury, or 30.35 milligrams per liter. You've heard on the weather. The relative humidity is 40%. It's 40% of that number then. 40% of 30.35 milligrams per liter. Or if they said it's 90% humidity, what does it feel like? Really muggy, really wet, because we're close to that number. Okay? When it gets to 100%, what happens? It rains. Because now the capacity exceeds the content. There's more than we can put in there. We'll come back and visit this, though. And yes, you would never need to memorize this. I would give you this chart. What? You give me that hairy eyeball. So here I have examples where I'm at two different temperatures, everything else is equal. Here I subtract 47 degrees. Here, because my body temperature is a little bit less, I only subtract 35.7. Where did I get that 35.7? From the chart. 32, 35.7. Okay. For our purposes, typically we just consider the patient to be normothermic. This makes life easier when we're calculating the alveolar air equation. So what am I told here? I'm told an FiO2, 0.3, told a barometric pressure, 738. I'm told a temp, 28 degrees. So what I would need to do is go back to that chart and see what 28 degrees is as far as the partial pressure. 28.3. Subtract off my 28.3, multiply it times 0.3, and I find it's 213. See where this is coming from? Now, if your patient has a body temperature of 28, you're in a world of hurt. Unless it's a snake.
This isn't Dalton.
It's an application of Daltons. Still. Because I have a total pressure. I'm looking at what else makes up that. Yeah, absolutely. And this is just showing as we inspire we've seen this before, but as we inspire the gas in, there now is the presence of carbon dioxide. There now is the presence of water vapor, and we got to account for those two. So the partial pressure of oxygen falls as it goes from outside to in. And that's kind of what this is just showing. We'll leave it at that. We know how to calculate the alveolar air equation. I think we did that today, didn't we, Dan? And that 0.8 that is there, again, is something called the respiratory exchange ratio or the respiratory quotient. Technically, they're different, but for our purposes, we're going to use them interchangeably. We can actually measure this. The measurement of the carbon dioxide, not that you need to know this, please don't write that down, but we can actually measure how much carbon dioxide our body is producing, how much oxygen our body is consuming. The ratio of those two is called the respiratory exchange ratio.
You want normal value?
No. So for well, you should know this one. This is fair game. Right? Normal PaCO2. I know what I wanted to say here. 0.8 for right now is what we're going to use as a constant, but recognize that will change as we go along next year. And there's my alveolar, and we know there's multiple structures that it has to pass through. I don't know why I have this, except it looks pretty cool. Once it gets across, then I have a normal value within the arterial blood system, 80 to 100 millimeters of mercury. Okay. What if I told you the PaO2 is 90 millimeters of mercury? What do you think about that value? It's normal. What if I told you the FiO2 that was needed to accomplish that was 0.9, 90%. That's pretty bad, isn't it? Yeah. So we need to kind of evaluate any PaO2 based upon what the FiO2 that's being used to accomplish it. There's 3 different ways we can end up doing this. something called the AADO2, something called the PaO2 to PaO2 ratio, and something called the PaO2 to FiO2 ratio. Let's talk about them. First of all, P big AO2 is what? Thank you very much. P small AO2 is what? So what is the difference from what is in the alveolus to what is in the bloodstream? And this is called alveolar arterial difference of oxygen, AADO2. You may also hear AA gradient. What's the push of that oxygen from alveolus to artery? Mm-hmm. Alveolar arterial difference in oxygen. The D stands for difference. Yahoo. And yeah, I probably won't ask you to memorize this yet, but you will eventually, so just file that away. Normal values, very, very small. There's not a whole lot of difference between what's in the alveolus and what's in the arterial system under normal conditions.
You're going to have a range.
Yeah, it's a little bit of a range in there. 5 to 20 on room air. Yours says 5 to 15? Okay. If I gave you an AA gradient that was 200, that's not good. Here's the problem with this value, is your values change, the normals change depending upon the FiO2. Really? That sucks. That's a medical term, by the way. So let's go ahead and take a look at an example of this. My arterial value is 70. I give you a barometric pressure, a PaCO2, an RQ, and FiO2, so we can calculate out what the AA gradient is. And we find that the alveolar value is 97. I then take my 97 minus my 70, and I get 27. Okay? So on room air, we said the normal was somewhere between 5 and 15, 5 and 20. I'm at 27. A little bit elevated. A little bit of a problem. And how do I know I got a little bit of a problem? What's my normal room air blood PaO2? 80 to 100. Where am I at? 70. A little bit low. A little bit of a problem. Everybody see where I'm going with that? Given that kind of information, you should be able to calculate an AADO2. And tell me to some extent whether that's normal or not. A little bit off. Oh, wait, I got 2 more to kill you with.
I have a question.
Yeah.
So you said that 27 is low?
27 is higher than normal,
Right.
so there's a little bit of a problem.
Right.
Means it's taking a little bit more push to get it across.
Right.
I'm losing a little bit more in translation getting from point A to point B than I should.
Where did you get 97 to
97
70?
is my alveolar air. I'm sorry, yeah, the P capital AO2. 70 is my arterial.
Okay.
And all I'm doing is looking for the difference between them. Normally it should be negligible, 5, something along that line. There should not be a big drop between what's in the alveolus and what's in the artery. We're only talking about a small couple of microns to move. Yeah.
When you say push, Are you kind of pushing
The gradient. The gradient across, yes.
Okay.
If there's a big, big number there, that's a bad, bad thing. Big is bad. I won't go any further. Another way to look at this, because one wasn't enough. This is the AA ratio, meaning the arterial divided by the alveolar. Conceptually, what percentage of gas in the alveolus is getting across to the arterial system? Normal value is somewhere around 75% and higher. Pretty much a good portion, 3/4 of what's in my alveolus should be able to get across to my arterial system. Doing the calculation on this one, I still have my same 97 for my alveolar, 70 for my arterial. If I do the math on there, it's about 72%. Normal's 75 and higher, just a little bit below that. So both the A gradient and the A ratio gave us the same picture. A little bit short. Not doing as good as I'd like to see them do. Something's wrong pathophysiologically. Oh boy, big word. Something's wrong with the lungs someplace, and we're not allowing this to happen. Last one. Whew, thank God. This is called the Piaf ratio. And at the bedside, this is the one we use the most. Why? Because I don't have to calculate that damn alveolar value. Thank God. All I do is just divide the arterial value by the fractional concentration. And if I do it with my little example, I find it's 333, where my normal is somewhere around 400 to 500. I'm a little bit short. So all three of them give us the same picture. There's some little deficit with my ability to adequately transfer oxygen.
Have you got that FiO2 from the test, or just normal fraction concentration?
It's a given. I would have to give that to you, or tell you the patient's on room air and you would use 0.21.
That's why it's used in the bedside.
Yeah, but if I have a patient, well, let's go back to that example I used earlier. My FiO2 was 90 on 0.9. I'm sorry. My PaO2 was 90 on an FiO2 of 90%. My ratio is 100. Normal is 400 to 500. Very bad. Just a way of evaluating how well are we oxygenating for a given oxygen percentage. And normally, if I put you on 100% oxygen, your PO2 should be 550, 600. So your ratio would end up being 550, 600. Anything over 400, we're happy. Below that, we start getting into having ARDS, or one of the major causes that we'll find at the bedside is ARDS. But more on that later. Don't you love how I just turf stuff to other people?
Would we still also use this to find when you're extubating?
Say that again?
Would you also use this if you're extubating to find out?
It's one of the things you could use to evaluate whether or not the patient's is ready to be liberated from the ventilator, ready to be extubated. Yes, all that is true. If my oxygenation protocol is working, Any one of those three could be used. What I want you, the major point I want you to take home is that if I have a PO2 of 90, doesn't necessarily mean that everything is hunky-dory. Depends what the FiO2 is you need to get to that point is.
So if it was 90 at room air,
We're fine.
it'd be fine.
Yeah. If you do the math on that, 90 divided by 0.21, I'll bet you it'll be close to 450. And yes, I like that slide. But I like this one better. Let's stop there.